Okay, let me have everyone's attention. One of the problems of not collecting the homework right at the beginning is that everybody works on it throughout the lecture. So please don't do that. I'll give you some time. If we can get done by 20 after, 25 after, you'll have some time. But if you try to finish that right now, or just concentrate on doing that, then you'll miss this other stuff. We introduced oxidation. I don't know if we went much further than this. To just say, in general, a primary alcohol reacts to form an aldehyde, a secondary reacts to form a ketone, and a tertiary does not react. I'll add one other little layer here, is that a primary, can form an aldehyde, but it can go on and oxidize further to form a carboxylic acid. All right, the primary can. The ketone, the secondary alcohol produces a ketone and does not go any further, and a tertiary alcohol does not even oxidize. All right. Here is a slide that I would like you to appreciate. It will show up here in chapter 12. We'll show it again when we get to aldehydes in chapter 13. We'll show it again in chapter 14 when we get to carboxylic acids. But you should become familiar with these two definitions of what oxidation and reduction is when we think in terms of organic molecules. In 1305, we said that the oil rig, oxidation is the loss of electrons, reduction is the gain of electrons, which is also true. But when we're looking at organic molecules, this is what we look at. So we're going to compare an alcohol to an alkane. And what's oxidation? Oxidation is the gaining of oxygen or the loss of hydrogen. So if we look at the alkane and then see if it were to convert into an alcohol, what has it gained or lost? It gained an oxygen. So this molecule gained an oxygen relative to go from here to here. It gained an oxygen. So what would that be? Oxidation. So to get from the alkane to here, you have to oxidize the alkane. Now let's take a look at the aldehyde. To go from an alcohol to an aldehyde, what has happened? Lost hydrogen. How many? 2 hydrogens. So what is that? That's oxidation. That's oxidation. Gaining of oxygen or the loss of hydrogen is oxidation. Now let's look at an aldehyde becoming a carboxylic acid. What has happened? What's changed? This has 2 oxygens. This only has 1. It has 2 oxygens and a hydrogen. We got 1 oxygen and a hydrogen. So this has gained another oxygen. So that's why across the top here I'm saying to move from an alkane to an alcohol to an aldehyde to a carboxylic acid is oxidation. Boom, 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 boom. You're oxidizing. And to move back in this direction, if you did reactions that removed an oxygen, added 2 hydrogens, got rid of that oxygen, you would be successively reducing the molecule. This direction is reduction, that direction is oxidation. And so we're talking now about the oxidation of alcohols. And so we're going to look at the oxidation of alcohols. This here is a primary alcohol forming an aldehyde. So here's a primary alcohol. Yeah, okay. I was going to kind of scratch this molecule off over here. But this is 1-propanol. It is a primary alcohol, 1-propanol. And if you oxidized it with a mild oxidizing agent, chromate, so that this is referring to this actually, chromate, and that's a solvent, pyridine, kind of a putrid organic solvent. If you did this under mild conditions with a moderate or a mild oxidizing agent, you could make an aldehyde out of it. Over here we got an aldehyde. If you hit it with a strong oxidizing agent like potassium permanganate, that's what this O is representing here. You could get it. It would go through an aldehyde, but it wouldn't stop there. It would oxidize it all the way to the carboxylic acid.
Mr. Rick, how do we know by looking at something that it's an aldehyde or a ketone?
Yeah, that's the whole point of chapter 13. But let's just cover it real quickly, because you do kind of need to know that here. Both of them have a carbon-oxygen double bond. So let's take that. That's going to be, that's an aldehyde. Let's take another molecule with 3 carbons on it. This is a ketone. So an aldehyde, the carbon-oxygen double bond is always on the end. The aldehyde is on the end. And a ketone, it's not on the end. It doesn't have to be smack dab in the middle of the molecule, but it's somewhere along the chain. And that's a ketone. And what you're going to see with an aldehyde, there's always a hydrogen. Well, yeah, pretty much. There's always a hydrogen right there, typically with a ketone. And a primary alcohol is oxidizing to form this, and a secondary alcohol is oxidizing to form this. Okay, and that should make a lot of sense here in a second, because remember, a secondary alcohol, there's where the OH is. All right? So the oxygen is not moving. Where the oxygen is where the carbon-oxygen double bond is going to be formed. So that this bond doesn't break. You just get another. So you got that original bond, and you get another bond formed. So the oxygen doesn't move, but it does change its nature from being an OH group to being a carbon-oxygen double bond. So a ketone is different from an alcohol. So this is just this case right here. Here's isopropyl alcohol, and you're oxidizing it, and you're forming this ketone. Now, I'm not worrying about the names of these ketones and these aldehydes right now. And on one exam, a question snuck in there. It said, finish the reaction of the oxidation of this alcohol and name the product. And the product was an aldehyde or a ketone. You shouldn't be, I won't be asking you that question. Shouldn't be. And if it turns out, I'll probably drop that question, because it's not until chapter 13 that I expect you to name aldehydes and ketones. Okay? So you don't need to name these aldehydes and ketones that form on your homework here. You just need to be able to draw the major aldehyde or the major ketone or whatever's going on. But don't worry about naming it. We'll name them when we get to chapter 13. You can see in organic chemistry, you can't just be in this silo that says, okay, we're talking about alcohols, we're not going to talk about anything else. When we talk about reactions of them, we got to start talking about aldehydes and ketones. Alkenes. When we looked at the hydration of alkenes, we had to start talking about alcohols. Okay, and here is a tertiary alcohol. No reaction. All right? It's always kind of neat to have one simple one. Just remember that. Tertiaries. Well, let me give you an alcohol, and you give me the. Let's oxidize this alcohol. So I want you to draw the product of the oxidation of that alcohol. I don't know if that's on your homework or not.
So you dropped an H.
What's the first question you have to ask yourself if you're being asked to oxidize an alcohol? Yeah, what class is it? What class alcohol is this? That's the very first question. What class is this? Secondary. Okay? Don't be thrown off. There's a methyl group over there, but it's not on that carbon that has the OH group. So this is a secondary alcohol. So what is it going to produce? Yeah, I'm looking at you. No. That's why I warned her around the class like this. I'm not trying to make you feel uncomfortable. I'm just, in the Army they have to call you to attention, right? So, what are we going to get? What do you got? Okay, that's good. All right? I got something like this. Yes?
Yeah, so you just replace the OH with an oxygen double bond.
Yeah.
Is it plus H2?
No, let's see. You don't have to show it because Stephen, it gets a little more complicated. Sometimes the potassium permanganate, it gets reduced down to manganese dioxide and maybe some water or potassium hydroxide, or so you don't really. But it's getting off of there. 2 hydrogens are coming off of there and going somewhere. It's not coming off as hydrogen.
On the homework, we don't have to write plus H2O.
No, not for this oxidation reaction. Don't have to. I wouldn't count it off if it's there. Don't worry about it. Yeah, in some reactions, I do want you to worry about it. If you're hydrating an alkene, I'd like to see a water molecule reacting with an alkene. And on the next reaction where we're dehydrating an alcohol, I'd like to see a water molecule being produced. Okay, yes?
Are you concerned at all of the angle of it? Or?
No. No, not right now. You can draw them just straight across. I'm going to move on now from here to here. The dehydration of alcohols. I think this is problem number 4, but let's understand it. It is, you've already been introduced to a substitution reaction, halogenation of alkanes, and addition reactions, hydrogenation of alkenes, and now an elimination reaction, where from a molecule we're going to eliminate, and in this case we're going to eliminate a water molecule. You can see why it's called dehydration. We're going to dehydrate the molecule by stripping out a water molecule. We'll come back and read this in a minute. Zaitsev's rule. Let me give you an example of this elimination reaction where Zaitsev's rule is not relevant. Why is it not? Well, let me just show you. Let's take this alcohol. These other lines right here are all hydrogens. I'm not writing all those hydrogens. We're going to dehydrate this thing, and it's going to give off a water molecule. Water is H2O. That hydroxyl group is at 1 O and 1 H. All it needs is another H to become water. The only place it can get that H is from an adjacent carbon. Okay? This OH is stuck right here on the end. There is only one adjacent carbon. There's the water. Now, the way this goes, if you remember how I showed you the addition reactions before, that bond between the carbon and the hydrogen is sharing 2 electrons. The bond between the carbon and the OH is sharing 2 electrons. So what happens here is these 2 electrons go up in there and form a double bond. And these 2 electrons drop down into here and form an HO bond with an OH, which makes water. Okay? See that? So what is the product over here? The product over here is this. Notice up there we got 1, 2, 3, 4, 5, 6 lines. 1, 2, 3, 4, 5, 6 lines. We formed a double bond and a water. We eliminated a water molecule from propanol, 1 propanol. Eliminated a water molecule. Okay, Zaitsev's rule isn't even applicable here. You don't even have to worry about it. Why? There is no other thing, no other way this reaction could proceed. So let's take another molecule as a different example. Let's take this molecule. And let's put an OH right there. And this time I'm going to put those hydrogens, and these other lines are all other hydrogens. There are 2 different ways in which I could eliminate a water molecule from this molecule. You could get a water molecule right there, or you could get a water molecule right there. Remember what I told you. The OH it can only leave with the hydrogen on an adjacent carbon. But this has a carbon on each side of the OH. So if this comes off of there, I'm going to get this. Okay? The double bond is going to form right up in there. Plus water. And if I eliminate this one, I'm going to get that plus water. Does everybody see that? There are 2 possible products. So now the question becomes, is it 50-50? How much do you get of each one? And this is the major product. And this is the minor. There is a major and minor product when you dehydrate that alcohol. This is the major. How would we know that? Well, you'd have to apply Zaitsev's rule. Let's go read it. Zaitsev's rule. The product that gives, the highest number of carbons attached to the double bond, that's your major product. Just remember that. Highest number of carbons attached to the double bond is going to be the more stable and therefore the more the major product. You will also see, the highest number of carbons attached to the double bond.
So is it typically more toward the center of a molecule versus an end?
Yeah, I think typically that would be true. Now, where did my molecule go? I lost my molecule. It's coming. I used to be able to move this around with my fingers, but yesterday I hit something, and all I can do is write with my fingers. You know how Word sometimes helps you, or you don't like its help? Yeah. Okay, so let's look at this double bond. It has that carbon attached to it and that carbon. There are two carbons attached to it. This double bond, now I'm not going to count these two carbons. I'm only counting the carbon that is directly attached to the double bond. So this one only has one carbon, and the other three lines there are all hydrogens. And notice here, we got two carbons and we have two hydrogens. So this is the more substituted double bond. This is the less substituted double bond. That's the minor, more substituted major product by Zaitsev's rule. All right, here's another example. Again, we got butanol here. This is 2-butanol. It's 3-methyl-2-butanol. That's what we have here. 3-methyl-2-butanol. I really like structural formulas, because here's your OH. You've got an H here. You've got an H here. You got a methyl here. All right? So you could eliminate that and get the double bond there. If I can move this down just a little bit. All right, so you could eliminate this here and get that, or you could eliminate this right here and get the top product. You see, you're going to form a double bond right there. But if you put the double bond right here, you got 1, 2, 3 carbons attached to that double bond. So this is by far the major product, the more stable alkene that's being produced. And this is by far the major product, and that other one would be minor. There's only one carbon here. Even though you see an isopropyl group there, it's got 3 carbons on it. There's only one carbon attached to the carbons that have the double bond. There are no carbons on this side, none, and one over here, compared to 3 attached to that double bond. Yes?
So if the OH was on the end, would it be forced to be that double bond?
Yeah. If this OH was here, even though there is an opportunity for even though this double bond would be more stable, there's only one choice. The OH here could only leave with that hydrogen and only form the double bond at the end.
So that means there's no major or minor.
That's right. There's no major and minor. There's only one product. So if the OH is on the end, you're going to only get one product. It's when the OH is in the middle of the chain that you have to start thinking about the various possibilities. And then which one would be the major possibility.
And wait, on the minor product, this example up there, there's only one carbon attached to what the double bond is?
Yeah, right here you got this double bond. You only have one carbon
Yeah, okay.
pumping into this double bond. Okay, so that's enough with Zaitsev's rule. Come back and look at this one. Just look at this one as another example and convince yourself that this is going to be the major product. What's the other possibility? The other possibility is that the double bond would be right here. But that is a more substituted double bond. I'll just leave that one for you to come back and look at. Okay. Now, I'm going to talk about dehydration again. Dehydration. This is the removal of water. Number 2 here that we just covered is the removal of water from a molecule. Down here, we're going to look at how you can remove a water molecule between 2 alcohol molecules. Let me give you a very simple example. And what we're talking about here are ethers. And I know I have a lot of verbiage on the slides. You can go back and look at it. That is an ether. A carbon-oxygen-carbon bond is an ether. When a dentist uses ether on you, he's used a certain kind of ether. Just like alcohol in alcoholic beverages is a certain kind of alcohol. There are lots of ethers. Wherever you have a carbon-oxygen-carbon functional group, you have an ether in the molecule. So let's take the simplest alcohol there is, and that's methanol. And let's look at 2 methanol molecules. And we could dehydrate or remove water from between 2 molecules. Oh, I'm sorry. Sorry about that. Okay, so we can remove a water molecule there. And what are you going to get? You're going to get that and that. See, we're getting rid of all the hydrogens, one of the oxygens, and we're leaving one oxygen behind. And we got that ether. And there's about the simplest ether you can get, plus this water. All right? It's elimination of water from between 2 molecules. You form an ether, and we'll look at the names of ethers in a second. But you could decide, well, I want to do this reaction with methanol, and I want to react it with ethanol, and form a certain kind of ether. And it would proceed the same exact way, dehydrate the water. Yes.
You don't need to have 4 bonds on the oxygen in the middle?
No. No, oxygen has only 2 bonds. Look at water. Nitrogen has 3 bonds, and carbon has 4 bonds. So no, you don't need 4. You don't want 4 bonds on that oxygen. Yeah, only 2 bonds, and even in your alcohol, see, the oxygen only has 2 bonds. When you have an OH group on a molecule, the oxygen is bonded to a carbon, it's bonded to a hydrogen, and it's done. Okay, that's a little bit of a reaction summary. There's another one. Oh, these slides are in a little bit. Let's stick with the ethers for a second, and I'll come back to the phenol. All right, so a little bit more about ethers. Yes. Yes.
So the way that you would, it's about the one that you just wrote. So the way you would write that, if it was, well, do you have the picture still?
Probably.
Like this? Yeah. So I was just gonna ask, the way you would write it, would it be COCC, like the one on the bottom?
This one?
No, the one on the bottom. Because you wrote that one and turned it to C. So that one would be COCC.
Yes. Yeah, and we'll look at the names of those. So that would be another ether.
That would have had a plus H2.
What?
Would also have a plus H2.
Yeah, right. So there's your kind of general formula where R is any kind of organic thing, whether it be a phenyl group or a pentane or whatever. This is diethyl ether right here. This is kind of looking at properties. I wouldn't worry too much about this. I did show you earlier where if you compared an alkane to an alcohol, you had a dramatic difference in boiling points. Why? Because you got a hydrogen on an oxygen, and it can hydrogen bond. What this slide is kind of pointing out to you is that there's no hydrogen on that oxygen. So there's no polar OH bond. So this is a lot less polar. It's pretty non-polar compared to an alcohol. And yeah, it raises the boiling point a little bit, 10 degrees or 8, 9 degrees. But it's not like an alcohol. It's not going to be as soluble in water as an alcohol is going to be. That's the point of that slide. But it does introduce you to another point, and that is this. Well, the naming of alcohol, of ethers. Yeah, here we go. Simple ones like we just saw a minute ago. If we had a methyl group on each side of an oxygen, just dimethyl ether. It's an ether. There's a carbon-oxygen-carbon bond. What's on either side of it? Well, there's a methyl on one side, there's a methyl on the other side. It's dimethyl ether. That one earlier there would have been methyl ethyl ether.
Oh, why is that dimethyl?
This one?
Yeah.
There's a methyl, and there's a methyl.
So it's ether because of the oxygen?
It's ether because there's a carbon-oxygen-carbon bond. That's the ether part of it. And what's on either side of that bond is two methyl groups. So over here, we have a carbon-oxygen-carbon bond. On one side of it, we have a methyl. And on the other side of it, we have an isopropyl. And so it's isopropyl methyl ether. Okay, let's look at this one. Okay, there's a phenyl group, and there is an ethyl group. So ethyl phenyl ether.
One of our 3x5.
Okay.
Yes. It's a benzene ring as a substituent, and that's a phenyl group.
Oh, any benzene ring.
Any benzene ring that's a phenyl group. Whenever you see the benzene ring, if you see the benzene ring all by itself, it's benzene. But if it's attached to something like that is, then we call it phenyl. Just look like right here. We've got a methyl attached to this oxygen. We're still going to call that a methyl group. We'll call that a phenyl group. Okay, now let's go one step deeper. Now there is a methyl and there is a pentyl. And you say, well, why don't we just call that methyl pentyl ether? Well, okay, that's a good question. Here's a pentyl and there's a methyl. See, it starts getting confusing. I'm up to 5 carbons. 1, 2, 3, 4, 5 carbons. And this carbon-oxygen-carbon bond could be between the methyl and the first carbon, or between the methyl and the third carbon. So just to call it methyl pentyl ether isn't clear enough. So what we do to handle that is we call this a methoxy substituent. All right, it's a methyl with an oxygen, methoxy. And where is it? It's on carbon number 3. So this would be 3-methoxy pentane to distinguish it from 1-methoxy. So instead of a methyl group here, this is your methoxy substituent.
How is that on the third one?
1, 2, 3.
No, but did you get that from the water?
No, I'm getting this.
It's doing something completely different other than that.
This is different from that.
Right.
Oh,
These are 2 different molecules. This is number 1. That's number 1. 1, 2. I'm going a little too fast here. This is carbon number 1, carbon number 2, 3, 4, and 5. So that is 1-methoxypentane. This is 3-methoxypentane. And if we had this group, we would call it an ethoxy. Don't go any further than that. I mean, don't say, well, what if we had fun? Don't get any more complicated than that. I basically want you to understand how to recognize an ether. You should be able to name a simple ether like dimethyl ether or diethyl ether. Most organic labs will have cans of diethyl ether in there. Highly flammable and a good solvent. So that it's very common. And actually diethyl ether is an anesthetic. So the fumes from it, I'm getting kind of drowsy here. Okay, you are. You leave it in the hood. Dentists use diethyl ether as one form of antiseptic. I'm going to just say omit this reaction. You can burn ethers. I just got done saying. This one is, what is the name of that ether?
Diethyl.
That's diethyl ether. That's the solvent in the labs. I said it's highly flammable. It is. It'll burn. But don't worry too much. I mean, that's just a combustion of an ether. We're not going to worry about that reaction. This is just some more examples. Here's some of the anesthetics. So there's diethyl ether. That was the very first one used. There's penthrane. There's a carbon-oxygen-carbon bond right here. So you got a methyl group, and you have this ethyl group, but it's got 2 fluorines and 2 chlorines on it. Penthrane. That's another anesthetic. I skipped. Let me go back to phenol for a second. Whoa. Phenol. All right. We're going to move from ethers to something else in a minute. Let's look at phenol, not to be confused with phenol. This is phenol. This is a molecule. You should have a 3x5 card of this one. It's an aromatic alcohol. and what it's called, phenol. There are derivatives of it. So there's phenol, hexachlorophene, an antiseptic, hexyl resorcinol, some of these things you've heard. There's a tongue twister, orthophenylphenol. All right, so this has both things in it. There's your phenol, and there is your phenol, and it's in the ortho position. Did I ever tell you about ortho, meta, and para? I didn't do that, did I?
We can skip it. We don't need that.
Ortho, meta, and para. We'll put that in the bin. There's the bin. If we get done with chapter 12, we'll go to the bin by 1:30. All right, so omit this. Don't worry about the reaction of phenol. We covered the ethers. All right, thiols. What is a thiol? It is an organic compound that has an SH group on it. Now look at where oxygen and sulfur are, right here on the periodic table. OH, an OH group forms an alcohol. An SH group forms a thiol. So if you have an SH group, you don't need to worry too much about naming these. I want you, there could be a question that says, which of the following functional groups is a thiol? You have an OH, I could have an NH2, an SH, a carbon-oxygen double bond.
Pick the one with the SH in it.
Pick the one with the SH in it. If I had 5 organic compounds, I said, which one of these organic compounds is a thiol? You're going to hunt for one that has an SH group on it. Okay? It's a thiol. It's not an alcohol, it's a thiol. Thiols and scent. Thiols stink to high heaven. Pepe Le Pew. This is Valentine's Day. He's heading off to see Pepe Le, whatever her name is. And then the sweetheart of Pepe Le Pew, you know, is a cat. Have you seen the cartoons? Yeah. It's a cat. Okay, it's a cat. So he thinks he's really smell good. You know, he doesn't notice himself. Everybody else does. But this is what Pepe makes, as thiols. All right? Natural gas, methane, is odorless. CPS Energy puts, anybody who's distributing methane gas, puts thiols in the gas at part per trillion levels. So you don't have to put very much in there. But if there is a gas leak, you're going to smell it. You go, I smell gas. No, you smell thiol. That's what you smell.
Sulfur.
Yeah, it's sulfur. It's sulfur with a hydrogen on it. H2S, so water is H2O. H2S is hydrogen sulfide. When you leave an egg to rot, the sulfur in the protein is being converted to hydrogen sulfide. And so it's giving off these H2S fumes. So the rose has alcohols coming off of it, and they're fragrant. Pepe Le Pew has thiols coming off of him, and they're not fragrant.
Does it matter if you put SH or HS? Because like this first one has HS, and then your second one over here has SH.
Well, what it's kind of showing you is that it's the sulfur that's bonded to the carbon. It's the sulfur that's bonded to the carbon. That's why they flip them around. You'll see me do that. I'll write an alcohol this way, or I will write an alcohol this way. I always orient the oxygen towards the carbon.
So just make sure it's,
I wouldn't get picky over that. People,
But it doesn't matter.
it doesn't matter. But that's why you're seeing them flipped around, because the chemist is saying this is the bond. It's a carbon-oxygen bond. It's not a carbon-hydrogen bond. It's a carbon-oxygen bond. But don't worry about it. Okay. Lower priority, naming thiols. Like I said, just be able to pick out a thiol from something else. We'll come to this in chapter 18, because that is an amino acid, cysteine, and it has ASH on it. Very important amino acid, an essential amino acid, and it can form these disulfide bridges, but don't worry about that. We'll get to that in chapter 18. It's just showing you here how that gets into protein, reaction summary. Here it is in words. Oh, does that pretty much have what I have over there? How do you prepare it? You hydrate alkenes. We hardly mentioned this, but that's what they're talking about here. They're talking about the hydrogenation of aldehydes or ketones, and that will form a primary alcohol, and that will form a secondary alcohol. That's not on the homework. We will definitely get into this in chapter 13. This will be an important reaction in chapter 13. I don't think it's on this exam. Because I know we're going to get to it in 13, I think I kind of skim over this, but this will come up in chapter 13. And then we got the dehydration here that's going to form an alkene. We have the dehydration that's going to form an ether. And then we have the oxidation reaction. Those are the primary reactions. There's always a slide like this at the end of the chapter that summarizes those reactions. So you got the preparation, the dehydration to an ether, and you've got the oxidation. Voila. Okay, to the bin. To the bin, and then we may be done a few minutes earlier than that.
Can we go back one slide real quick?
That one?
Yeah.
Let me get this ortho and metapara on this lecture. You done, Rick?
Yeah, good.
Okay, let's just talk about ortho metapara real quickly. Okay, I really should have covered this in chapter 11, but let's take this molecule here. Uh-oh, battery running low. All right, so we have that molecule there. With one methyl group on it, what's it called? If it just had one methyl group? Toluene. As soon as I hear it, toluene. Now we got two methyl groups on there, so I might say this is 1,2 dimethyl benzene. Or I might say that it's 2-methyl toluene. I could say it's 2-methyl toluene. And this one would be 1,3-dimethyl benzene. I actually like the, let's call it 2-methyl-toluene. I'm sorry. 2-methyl-toluene, and this would be 3-methyl-toluene.
Because the one right there makes it.
Yeah, the first one there makes it toluene. Okay, now the other naming for this, they would say, okay, on this benzene ring, that's going to be the ortho, the meta, and the para position. So instead of calling that 2-methyl-toluene, we're going to call that ortho-methyl-toluene. And this one, instead of calling that 3-methyl-toluene, we're going to call it meta-methyl-toluene.
So it's the position of the extra.
What's wrong? You're lost. Okay. All right, so on this, if we have a benzene ring and we have something right here, then this is going to be the ortho position to that. To the thing that's on the top is in carbon number 1 position. So 1 over from it is ortho, 2 over from it is meta, and completely on the other opposite side of this thing is para. Okay, now, let me give you an easy way to remember that, I think. Ortho, meta, para. What's that look like? A boot. Stomp. Stomp. So when you stomp on this thing, you go to the ortho, meta, and para positions. That's what you feel like doing, isn't it? All right, so that's it. All right, that was in the bin, and we're done with the bin. Finish chapter 12. What's the date today? 26th?
Yeah.
The more hydroxyl are on the second one, so it's going to be more polar. So it's going to be more solid soluble. The first one is another hydroxyl more soluble. And the first one's hexane, the second one's water.
How do you predict it?
I don't know. See, like the hypothesis, I don't know. Yeah.
I guess how you can test it putting it in.
And it has more than the first one.
Wait, y'all know the names of these though?
First one is
Do we have like the actual name for it?
I just put the first one in there. Mr. Rial, for question number 4, I just did the finishing product. Is that okay?
Yeah. Yeah, you don't have to write out the
Okay,
whole
because I like try to write out the whole thing over here, and I just barely have room. And I
Right. No. All I wanted to see is
Okay, so final product.
final product.
And then what's the common name for 1,3? Is that
So B would be isopropyl alcohol, and then the IUPAC name would be 2-propyl.
isopropyl alcohol?
I can't wait. You finished your last one? Yeah, me too. Wait, what else? Hydroxyl?
I will try. I'll definitely look at it and see if I have another lecture to put in there. Yeah, turn these in. Okay, don't leave yet. Do you have to leave? Okay, I was gonna. I don't know if we want to say anything about this. Do you have a team? Yeah. Okay, why don't you put your names on there? You won't know what your project is because you don't even know what the assignment is yet.
I'm gonna leave one of the
Yeah, I want to stay.
Yeah, we're overachieving.
Yeah. Maybe we should get a new team member.
You were late to study session last night and now you're here? Wow.
Could I have your attention?
You have one more
30 seconds.
Bye.
Let me have everyone's attention for 30 seconds. Dustin, 30 seconds. I asked you to come today and kind of sit near your team, right?
Oh, yeah.
We don't really have time to explain the project. What I'll try to do is get an email out, and I'll post a little PowerPoint on campus. It maybe have 4 slides on it. It won't be, you just go look at there. It says here's basic requirements for the project. But if you know who your team is and you want to record that right now, just pass it around and write the names of your team. 3 people max. And then we won't worry about explaining it right now, but at least we'll start knowing who the team is. So after the exam, you can kind of go look and say, well, what is this project?
I just gotta go get the paper and fill it out. We can go.
These others are secondary. Because the middle, there are 2 options. These require bits of remember that. So they're all identical.
Oh, that's what the.
They're identical.
If you want to, I guess like we can work it out.
So would this be, it would be O, not OH, right?
Oh.
When it turns into
Aldehyde. Carbon oxide.
you want
Thank
us
you.
to write the aldehyde or no?
No. You don't need to name that. In chapter 13, you'll learn how to name those.